All right, welcome back. Today we will study about the performance characteristics of instruments, or we can say performance characteristics of measuring systems. Uh, it's very important for us when we design or analyze instruments that what is the criteria actually to differentiate between a good instrument and a bad instrument, and which instrument can be really classified to be used in the industries, or which instruments can be okay for the domestic ones, because we have to finally trade off between the cost of the instrument and the performance of the instrument also. We cannot really make an instrument that is quite expensive at the domestic level, where we can actually take these performance low performance instruments also. But in the industries, in the application in the industries, we cannot really compromise on the quality. So there we need to actually make the performance very good. So what are the different types of performance criteria that are associated with the instruments? This is what we are actually going to study in this lecture. Now, obviously, to make an appropriate choice between various instruments that were available for a particular measurement task, for example, we have thermometers, different types of thermometers for measuring the temperature. Which instrument should we choose, or how do we design a new instrument actually for a particular task? The characteristics or the performance characteristics assumes a major criterion. So we have to actually specify what are the what is the performance of our instrument that we have designed, or what is the performance comparison of the two instruments that we have that is available for a basic particular task. Now, some of the applications involve measurement of quantities that are constant or vary slowly. For example, take an example of again measuring a temperature, or measuring a pressure of a gas or a liquid, which generally we expect does not vary actually too quickly, doesn't change too quickly. So for that, the quality of measurement actually is defined by the static characteristics of the instrument. But in applications where the measurement actually changes dynamically, the the value to be measured actually changes quite frequently. There, the instrument actually has to be carefully designed, and we have something called as dynamic characteristics of in the instruments, where the dynamic characteristic of the instrument actually takes a major role, whereby in the varying nature of the input and the constant the frequently varying or the rapidly varying nature of the quantities actually have to be actually, that effect has to be taken or catched into. So we need a dynamic relation between the instrument input and output, which is actually very important. So both static and dynamic characteristics of an instruments can be there, but they are generally studied one by one. So we study static and dynamic characteristics separately. That is what we will do here also. And the overall performance of the instrument can be judged by something called a semi-quantitative superposition of both the characteristics. Though some of the instruments may not really require dynamic characteristics to be studied, but some of them could be, would just require the static characteristics that would define their performance characteristics. But some instruments may require both of them. There could be some non-linear relations or non-linear inputs and something like that. There could be some varying kind of data from the input, where we need something called as simulations that can actually help us to basically characterize those types of instruments also, but this will not take up here. So all such characteristics like static and dynamic characteristics of any instrument are actually provided in the instrument data sheets, which is very important. We'll study towards the end of this lecture. We'll see some of the data sheets, and we'll see how actually they are specified by the manufacturer of those instruments. The quality or the characteristics of that instruments are actually provided. Now, these are the static characteristics that we generally see for any instrument. They may not be, defined for every instrument, but this is a broad category of the static characteristics. So we have linearity, sensitivity of measurement, zero drift, sensitivity, drift. We have hysteresis, dead space, threshold, backlash, accuracy, precision, repeatability, reproducibility, tolerance, range or span, and resolution. So we have these 11 characteristics that are generally studied for the instruments. We will see in this lecture only static characteristics. Dynamics or dynamic characteristics of the instruments, we'll see it in the next lecture. So we'll take it one by one. Now let's see about linearity and sensitivity of measurement. So what do we actually mean by linearity? So linearity, as per its definition, would refer to actually the relation between an input and output should be something called as linear. So let's take a very simple example of a say, weighing machine. So let's assume we are using a spring to measure the weight of an object placed on its hook, and let's assume this is the scale that is provided to us. This is arranged in such a way that this is a single unit. So the moment we load this spring with some weight here, W. All right. So accordingly, this scale would actually displace, sorry, this spring will actually displace down, and as per the stiffness of the spring. Now, if we add a weight of, or we take a weight of 10 kgs, for example, so accordingly there will be some displacement in the by the of the spring, and accordingly there will be a pointing of this on the scale. So let's say we have 10, and then for 20 kgs, as we add the weights, let's say we have 20. For 30 kgs, let's say we have 30, and similarly. So if we plot this input output characteristics here, so this is our input and this is our output. So for 10, let's say we have a 10, so we have this value. For 20 we have another one. For 30 we have like this. So if we plot this as a graph, so we'll see that this is almost linear. The relation between input and output is actually linear. But this doesn't really happen with the instruments if the quality is not good, because this highly depends on the spring quality here, because spring is the only element of this instrument. So the spring quality is actually very important. If the spring quality is not good, then it may not be really linear, and you may see that at 10 kgs it may show us 10 in the scale, but at 20 it may show us only 19, and at 30 it may show 31. So it is kind of a non-linear, so it may turn out to be something like this, which is a non-linear one. So a red curve here is non-linear, but we would like the instruments to be more linear actually, so that we can predict, and we can actually always predict for a different output what could input, what could be the outputs. So instruments are generally preferred to be having a linear nature with a linear relation with the input and output, but it could be a non-linear characteristics also. So it will depend on the quality of the instrument, that whether it's you really are able to maintain a linear relation or not. It could always be a case where you can actually define. There are instances where we define instruments. Suppose we have a relation like this between input and output. So you generally say that okay, this is linear from this range to this range. Okay, so you can say that this is linear from this range to this range. So if you want to operate this instrument, this will be quite linear from this value to this value. Let's say I1 to I2. This is generally called as the one of the static characteristics of the instrument. And the sensitivity of measurement is defined actually as the slope of this line, which is the relation between input and output. So because it could always be like this, could be highly sensitive, it could be something like this. The slope can be low, or the slope can be quite very high. For a very, very small change in the input, we have a considerable change in the output. So this is highly sensitive, and this is, let's say, moderately sensitive, or you can say it's quite low. Sensitivity is quite low, because for a lot of change in the input, you have a small change in the output. So this is sensitivity is actually very low. All right. So sensitivity of measurement actually defines the slope, or you can say the slope of the linearity curve. And linearity obviously is the how actually linear the relation between the input and output is. So instruments are generally preferred to be linear in nature, to have linearity in their characteristics, and if they are not, there may be some deviation from this linearity curve. So that is the percentage of, can say, the non-linearity present in the instruments that has to be specified. It's very important, because if you do want to take these measurements in industries, You cannot just rely on this type of instrument where you don't really expect. You expect at 20 kgs you should have a reading of 20. If it is 19, then you have an error. It's deviating, and at 30 you may have 31, so it's again deviating. So this is more of a non-linear nature. So you would like instruments to be designed which are actually more linear, which have a linear output. All right. So now there is something called a zero drift. Zero drift is a characteristics in the instruments where, because of some issues, maybe ambient conditions or because of some usage of the instrument, your instrument shows up a constant actually deviation between the output and the input. Though it may be linear, so it's input and this is output. So you may see something like this as the characteristics. So this part actually is called the zero drift. So at zero input, you still have an output, which is actually wrong. But what happens is this since this curve or this linearity is maintained by the instrument, it means this is something called as a bias, constant error or zero drift, constant error in the instrument. So what happens is at every point you have a constant error. So if you want to take an output reading at this point, so it may be something like this. You can always subtract this part from this value, getting a correct value. So this is kind of a shift in the actually the output values because of some calibration problems with the instrument, or because of some regular usage of the instrument. This generally happens. You must have seen the bathroom weighing scale that you use to measure your weight. You have a pointer and you stand on this. Say a human being stands on, then you must have seen the constant error. Actually, before even loading, you may see that there is some kgs, or you can say 5 kgs already shows. So what happens is after you weigh yourself, suppose you get to 75 kgs, so you assume that, okay, yes, this is actually 75 minus 5, so I'm just 70 kgs. So you easily subtract this part from here. So this is actually called as bias also, or it's also known as zero drift. And this is generally you can say corrected by means of something called as calibration. So you try to measure this value, and actually you sometimes have some facilities also to calibrate, whereby you move some screw and then you get this back to the zero at zero load. So such things are also present in the instruments where you may not really be aware of such things, but you may get. So if you're not aware about the zero drift in the instrument and you measure, you may say, oh, the weight has changed. So which is actually not true. So you should be aware that there might be some zero drift in the instrument. So zero drift is nothing but a constant shift in the, or a constant bias in the instrument output when there is no actually, well, sorry, constant, you can say constant shift in the instrument output, which actually prevails for the whole range of the instrument. Similarly, something called as sensitivity drift. Actually, what happens is because of the environmental changes, because an environment has an impact, the temperature and pressure has an impact, or other parameters have impact on the instrument, the instrument parts. So there might be something called as sensitivity drift, where the sensitivity of the instrument actually changes by some extent. So something like this we see. So if this was the original instrument that we had, so there was a linear relationship between the input and output, but because of change in the ambient conditions like temperature, which changes the suppose in electric circuit there's the resistance of the circuit, or it can change even the other features of the instrument. So because of that, what generally happens is this sensitivity actually changes for the instrument. So the sensitivity actually changes something like this. So which means the instrument has actually become more sensitive, or you can say the instrument has become less sensitive. So this thing has to be also, you should be also careful about while designing or analyzing these instruments. This is also provided in the instruments, and this may happen because of change in the ambient conditions. So you may be working with the instrument, you may be measuring some of the quantities, and you know that there is a linear relationship between the input and output, but you may take this instrument to a condition, to a condition like, you can say expose it to the environment where you have high temperature and all those conditions, and because of that there is a considerable change in the properties of the subcomponents of the instrument, and because of which actually you have change in the sensitivity. So you may get, for a same input, you may get different values of the output. So you have a higher value than this one. So you should be aware about this type of drift, and generally instrument manufacturers actually provide you with these details. Okay, that okay, if you change the standard conditions from this to some other conditions, and accordingly you will have a change in the sensitivity of the instrument. And then all these together actually can be something like can show in a graph like this, where sensitivity drift and zero drift are together. So this is the original one. With sensitivity with zero drift, it shifts here as a parallel line, and with sensitivity drift and zero drift, it shifts something like this. So with this basic shift, so let's say with short dash long dash, I'll draw it. This is how your graph will look like, where you have both sensitivity drift and the zero drift. These things are all generally specified by the manufacturers of the instruments, or if you want to design the instrument, you'll have to specify these things for an instrument if it really is there. Generally, these things are seen in the instruments, that these type of characteristics that in instruments actually exhibit. There's another phenomenon called as hysteresis. This is again, there with the some of the instruments, only not with everyone. So, for example, you have springs. In a normal pressure, I have just shown you again weight measuring. Spring. It could be something like this, or you can in the pressure gauge that we have seen. There is a pressure gauge where we basically measure the pressure of the liquid. There's a piston and there is a rod and there's a spring. So with these springs actually you have these issues where there is, you can say, spring, there is issue of friction, the issue of magnetism. In all such cases actually what happens is the loading and unloading curve is actually different. What it means is, you can just maybe show an example here. So suppose this is the loading and unloading curve. So this is output, this is the input. So what happens is, so for, let's say, output is for example the displacement, the input is force. Okay, so you say that you require some amount of force for displacing it by this much distance. Okay, you can say while while we try to actually elongate the spring. So spring, while we elongate the spring, actually may require some force to displace it by some distance. All right, so the moment we add the force up to a particular limit, there may be a displacement curve that the spring will actually follow. It may not be actually linear, it may be non-linear, because springs are actually called as, you can say, Hookean springs or linear springs up to a particular limit only, where it follows the Hooke's law, F is equal to kx. But after that, the springs generally become non-linear. So there is no linear relation between force and the displacement. So it's a non-linear relation where you may have x square or something like this. So springs are linear only up to a particular range. So let's assume there's a spring, or which is non-linear in nature. So it would follow some curve like this up to a particular force. Okay. Then the moment we unload this, so we remove these loads one by one, we reduce this force step by step. And what we generally see is that it doesn't really follow the same path. Rather, it follows a different path. So what it actually means is that you require, for the same force in the, you can say in the reverse phase, you have very small displacement. The output hasn't gone back. It hasn't actually reduced, to that displacement to this much. It's actually still here. But as you go on doing it, reducing the force, it will come to that point and come back to its original point. This phenomenon of having a different loading and unloading curve for some of these can say components of the instruments actually refers to hysteresis. This is also in case where there is friction involved. So there again we see some phenomena like this, and also in magnetism, where we see in iron cores, in case of in case of electric circuits where we have iron cores, in LVDTs we see this type of phenomenon or this type of problem is there. So a sensor like LVDT would always be specified with this characteristic of hysteresis. So this will be always specified. and for springs also, or some instruments involving springs, you also will be specified with this hysteresis characteristic. So this is a typical curve that we see for various such instruments. You have a loading and unloading curve. You can have always sometimes some negative inputs also. So you can say this is the measured variable or the input. So you can always have negative inputs, and for which you can have negative outputs. That could also be a case, or you can always take this as to be some other reference. And you see that there is a curve, variable is increasing, there you have an increasing output, but while decreasing you have a different curve. So there is some kind of storage of energy. So similarly, you have something called as maximum input hysteresis and maximum output hysteresis that happens with these systems. And you have something called as dead space. We'll talk about dead space later on. So this is actually the hysteresis. So you have to specify for your instrument actually what type of curve this will follow. Now let's talk about dead space and threshold. So in some instruments, you may have exhibit something like this, a behavior between input and output of the instrument, whereby after some point value of input only you will have change in the output. There are instruments where because of friction, because of their inertia, they may not respond to a very small amount of input. Only after some time they will actually respond and then have some linear or non-linear curves. Similarly, they may have the same in the negative range of the input, so something like this. So generally we show dead space as this area, or this kind of, you can say, this values of the inputs for which there is no output. We call this as dead space. This happens also in case of in case of actuator. I'll just give an example. For example, you have a DC motor with a 12-volt specification. So the moment you apply 6 volts or 7 volts to the DC motor as the voltage across the two ends, you will see the motor will not actually move. It may start moving at 7 volts, 8 volts, and 9 volts. At 12 volts, it may have some, it will move as per the desired specifications. It will have the current drawn will be, and the torque generated, the RPM generated would be as per specifications. If you just put 9, motor may still rotate, but not with the desired RPM and other things, and the desired not give the desired torque. But it doesn't really move with some, let's say, 5 volts. Why is it the case? Because we still apply some voltage across its conductor. There should be some motion, but because there is friction at the at the bearings of the motor, and because there is some inertia of the motor, for which you need to have minimum potential and minimum energy actually to make it across that barrier. So that's what we actually call as dead space in this case, or you can say threshold. Threshold is also it comes closely with dead space. So threshold is nothing but this actually point. You can say threshold is this point, the point actually the minimum energy that is to be that, or the minimum value of the input for which there is, and the change in the output. So this point actually is the threshold, and this gap actually we called as the dead space. So this gap is the dead space, and this point actually can be called as threshold. So this is one and the same thing. Threshold can be now defined as the minimum value of the input for which there is change in the output. All right, and dead space is that range of the input for which there is no change in the output. So yeah, now we have kind of understood. So even for a spring which is which is designed to weigh some 10 kgs to 100 kgs as the range specified. So if this is the specification by the manufacturer, so if you just put 5 kgs here, or maybe 1 kg, you may not see any displacement in the spring. So minimum of, let's say, even at 2 kgs nothing may happen, but maybe at 5 to 6 kgs this may start moving down or displace. So for 5 kg this may be even called as threshold for this. Okay, so this is how we define. Similarly for thermometer, you may have a temperature that it can measure, minimum temperature that it can measure, let's say maybe 10 degrees to 100 degrees Celsius, but you may even put a 1 degree in this, so you may not get anything as an output in the mercury. So but at 7 degrees it may still show some change in the level of the mercury, so that can be called as threshold. So this is the minimum value of the input required to cause a change in the output. Fine. Now this is to be again specified by the instrument manufacturer, these characteristics for the instrument that has been developed. There's another phenomenon. This is actually related to dead space again. This is known as backlash. This happens in gears. So when we have gears that are used to transmit motion, or meaning maybe other purposes that we use gears for, we generally see that if you have clearly understood or carefully understood the design of the gears, you have something a space that lifts out here. This is actually called as backlash. This is generally used in for actually you try to avoid something called undercutting here. You try to put up some oil here, lubricating oil here, so that there is the friction is the least, because these are mating parts. So you should avoid having too high as a friction, because that can wear out these gears easily. So you try to have put up some lubricating material here or oil here, so that this moves smoothly. So this space though is quite necessary, but it causes something called as backlash, or you can say this is the dead space. What does dead space means? So if now the gears are like this, so if this gears try to move, like let's say clockwise. So the moment it tries to move clockwise, and this is this is static. So what happens is, for this amount of distance that we have marked as backlash here, so for this amount of motion of the gear, there will be no change in the output. So this gear will not actually move. Only after this gear teeth actually touch the bottom gear teeth will the actually motion be transferred, or you can say the displacement of this will be there. But up to that point only, for this small distance, there will be no change in the output. So we will have something like this only after this part. So this is the backlash there. So backlash is again dead space, but it's more connected to gears. So in gears we call we have a term called backlash. We don't use dead space in gears, and we call it as backlash. So backlash is a phenomenon in gears that is actually the dead space for the instruments. So this is again what we call as non-linearity, because the input output curve in this case is something like this, or it may be like this. So this is not a linear curve between the 2 points or between the two. So this is a non-linear phenomenon, which is backlash or dead space. This one, this is a non-linear curve between the input and the output. Now we have something called as accuracy. Accuracy we define as it can be defined as the extent to which a reading might be wrong, but it's the maximum amount by which the result differs from the true value. So we have so we have the temperature specified as 100 degrees Celsius with an accuracy of, let's say, 10%. So what it means is that our temperature, if we have measured by the instrument, is 100 degrees Celsius, it cannot be less than 90 degrees Celsius, and it cannot be more than 110 degrees Celsius. So accuracy is defined even for the up to percentage of full scale reading of the instrument. So what it actually means is that if we want to measure a temperature of 100 degrees Celsius, we should use an instrument of this kind. But obviously, having an accuracy something like this, 1% would always be better for us. It will be that it cannot be 99 less than 99. It cannot be more than 101 degrees Celsius, which is actually quite good. So let's say this type of instrument is generally preferred. Let's say if we want to measure the temperature of human body, during the fever, so which is very important and critical. You cannot just put up to this level where you can really risk a patient that you don't really understood that the instrument is not able to actually measure the correctness. But in various other cases this may be suitable, but this is more preferable. And if it even goes to 0.5 percentage of full scale, this will be all much better than even that. So you will have 99.5 degrees Celsius as minimum, 100.5 degrees as the maximum deviation. So but as we go for higher accurate or can say higher degree of accuracy, obviously the cost of the instrument actually would increase. So in the industries we would like to have the instrument to have higher accuracies, which is actually specified as the percentage of full scale reading of the instrument. Similarly, you have something called as precision. Here accuracy is more related to the actually output. So here we are concerned with 100 degrees Celsius, and we are just talking about how close this is to the 100 degrees Celsius. So this should be clearly understood. And in the precision, this is a similar term to accuracy. We generally misinterpret accuracy and precision. Precision is actually different from accuracy. Precision is actually the the degree of closeness of the each output from an instrument. So for example, this could be understood by an a graph like this. For example, in case A, where we say it's low precision and low accuracy. So let's not talk about accuracy here. So let's say this is the target for the robot, where the robot is asked to actually put up the a block near this point. So what happens? The robot does it, put it here in the first instant, second instant here, third instant here, the fourth instant it puts here, in the fifth or sixth it puts at different instances. So in this case, we can say that the robot is trying to put it almost near to the the target, but at all the instances, all the six instances, the robot has actually had a kind of a scattered can say output, which means the all these points are actually at different locations. They are neither accurate, they are nor they are precise. So accurate means they are how close they are to the goal. So they are each of the can say each of the trial by the robot is actually different from the goal point. So it's not an accurate case. What does precision then mean? Precision, actually, here we can see a robot which is not accurate, but it is precise. So it is not closer to the target, but what is happening is that it is constantly trying to put up the blocks at the same point. So what it means for a designer or for an analyzer is that there is some constant bias or some constant shift in the robot calibration, because of which it is trying to put it repeatedly putting up the output at the same point, but it is having a constant shift. So this constant shift is generally because of bias, which can be removed by calibration. So the moment you calibrate the robot for this type of error, this will automatically put up all these things here. But what it actually helps us is in the definition of the precision. So precision is that in all the instances the robot has tried to put the job at the same place. So this type of output is more precise. This is what we call as precision. How actually the robot tries to put locate the same, or we can say the instrument that we use to measure temperature, pressure, or let's say velocity and other things. How accurate the instrument or how repeatedly the instrument gives us the same value, actually. That is being more precise. It may not be the correct value, but it is trying to give us the same value for repeated instances. So we are trying to measure the temperature or velocity of some object, and we are constantly, after so many measurements, getting the same value, which may not be close to the actual value, but if we are getting the same values, and that is called as precise instrument. And if we are getting it near to the actual target, and then it is all the other points are all at the same point, so we can say this is highly precise and highly accurate. This is also highly precise. You cannot say that this is just precise. This is highly precise because this is at the same point. So this is the difference between precision and accuracy in this case. Repeatability can be defined as the feature of the instrument whereby the instrument repeats, or you can say for the same conditions and for the same observer or for the same instrument, we get the same value for at different instances. But reproducibility actually differs from repeatability in a sense that how capable is the instrument actually to reproduce the same results at different conditions of environment, at different locations, by different persons. If that is the case, if it reproduces the same value, then we can say that the instrument has a higher reproducibility, which generally is not there, because as you change the conditions, the environment conditions, and different observers, they have different ways of measuring. So generally reproducibility may not be very good, but for good instruments reproducibility may be really good. Other characteristics are tolerance, that you may have heard about. Tolerance is specified in industries generally because that's where it really matters. This is the maximum value that is expected in the output value. This is closely related again to the accuracy. So accuracy and tolerance can be called as similar ones. So it is also in the industries the maximum deviation of the component from the specified value. You must have heard about tolerance in the electric resistors. You have tolerance band, you have some 10% tolerance, 5% tolerance in crankshafts, or in many other applications. In every application you see, tolerance is always specified. It's the maximum deviation or the maximum error that is expected from the output. So this is almost similar to accuracy. So you can say how accurate your this measurement is. So tolerance and accuracy in essence can be called as, can be synonymous. And then range and span. So you always specify the range of the instrument, which is very important. We cannot just allow the instrument to be used in all the instances. We have to specify the minimum and maximum values of the quantity that the instrument can measure actually. And then you have resolution. So these are all the static characteristics of the instrument. So resolution actually tells you the lower limit on the magnitude of change in the input quantity. So you must have seen in the for example, you have a speedometer, you have some divisions. Okay, so this division actually can say this finely divided scale actually, or the subdivisions, is the maximum, or sorry, is the minimum change that you can actually detect. All right. So in between, if there is some input which causes an in between kind of a movement of the pointer, it will be difficult to measure actually that type of value. So for instruments, manual ones also, it is difficult. But obviously these days we can have very high resolution instruments. We can measure a very small change in the output reading also. But if it's not having a good resolution, which means that for a small change in the input between the two values that are specified on the scale, we cannot actually measure the value. We cannot actually talk about the accuracy of this now, because it can either be this way or it can be this way. So the resolution is the lower limit. It is the lower limit on the magnitude of change in the input quantity that produces an observable change in the output, and it's actually more closely related to the division subdivision on the scale. Fine. So let's look at now some of the data sheets just to make you, aware about how important and how actually the practical implications are there. We'll just talk about temperature sensor, pressure sensor, accelerometer, and force sensing resistor. So this is an accelerometer data sheet by Analog Devices. So you have a 3-axis accelerometer. So let's see how it actually looks. These are the features. You have 3-axis sensing. It tells you about the features. It's a small package, low power, single supply operation, and then it excellent temperature stability. What actually I'm interested in telling you is specifications, and also some of the performances that are there with the accelerometer. Now these are the specifications. It tells you about the sensor input, the measurement range. The non-linearity, it tells you about percentage of full scale, tells you about the errors, tells you about the sensitivity, zero bias, the frequency response. Now these are all dynamic characteristics. All right, so this is how actually I wanted to just show you how actually all these things are actually mentioned for the instruments. Similarly, we have a force sensing resistor where we can just see that this is again an instrument actually to measure the amount of pressure, and accordingly it's converted to force. So they also specify the generally the specifications. You can just say the force, sensitivity, range, repeatability, resolution, in force, repeatability. And then you have actuation force, how much should be there, hysteresis, it tells you about the drift. All such things are actually specified. And similarly, you have a temperature sensor actually, which the data sheet is given from Texas Instruments. It also tells you about the non-linearity, tells you about the various features, the accuracy, the linearity, and all those things. So similarly, you can see the definitions of the different parameters actually that are put up here: accuracy, non-linearity in terms of the electrical characteristics of this instrument. So that's why they are very important. Actually, the instrumentation industry is quite you can say quite a big industry, and then these specifications are actually very important. And then example of a pressure sensor. So this is a integrated silicon pressure sensor on chip signal conditioned. So you can just see there is some features. Error talks about the error at different values of the temperatures, and then you have some specifications also, pressure range, operating characteristics, and then you have full scale outputs, accuracy, sensitivity, response time. So they are all specified. So this is volts per kilopascal, which means this is actually a slope between the pressure and the voltage that it gives us as the output. All right, so this was just about to give you an glimpse of actually different types of data sheets that are actually using these. So these are designers of these instruments. Again, for a user also, you can actually, you have to use these data sheets to understand when do you use these sensors for. The application of these sensors actually is very important, whereby basically you have to use them at particular places. What type of sensor is actually preferred, what type of sensor should be used, all these are actually very important.